This is lesson 4.1. Solve systems of linear equations with two variables. Our learning objectives are to determine whether an ordered pair is a solution of a system of equations, solve a system of linear equations by graphing, solve a system of equations by substitution, solve a system of equations by elimination, and choose the most convenient method to solve a system of linear equations. Great. Let's begin talking about determining whether or not an ordered pair is a solution of a system of equations. Well, what is a system of equations? When two or more linear equations are grouped together, they form a system of linear equations. In fact, here is a visual for you. Here I have curly brackets, and inside of that set of curly brackets, I have two linear equations. This is a system of linear equations. Okay? So how do we solve them? That's what today is all about. And first of all, what is a solution of a system of equations and what does it look like? Well, the values of the variables that make all the equations true. That is what a solution to a system of equations is. And a solution of a system of two linear equations is an ordered pair, x comma y. So our solution will look like this, where we have an x value and a y value, and you'll find those number values. Great. Well, let's start to get a little more comfortable with this. Okay, so example 4.1 says determine whether each ordered pair is a solution to the given system. Right? So if we want to check to see if a certain ordered pair, right, xy coordinate, is a solution to the system, we can take all of the x values of the system and plug in the x value of the coordinate, and then the y values and plug in the y value of the coordinate, right? So we replace all the x values with what x is and all the y values with what y is. And then we see if it makes the equation true, right? Does this side equal this side? Does this side equal this side? Okay, and so let's dive in and get comfortable with this. So I'm going to take this system and I'm going to rewrite it, but when I see an x value, I'm going to replace it with -2. And when I see a y value, I'm going to replace it with -1. So here I go. I start writing x, which is -2, minus y, which is -1, equals -1. And the second equation, I start writing 2x, replacing x with -2, minus y, which is -1, and set it equal to -5. And really, I'm questioning, is this true for both equations? Does the left-hand side equal the right-hand side? So let's clean it up. -2 plus 1 is -1. So I get something that says -1 equals -1. Well, that's a true statement. Yeah. Okay, let's look at the second equation. I have 2 times -2, which is -4, and then minus -1, which becomes a plus 1. And -4 plus 1 is -3. And I get a statement that says -3 equals -5. And that is not true. -3 does not equal -5. So I'm going to put an X right here just to show you guys, hey, that's not a true statement. And so what is our conclusion? Uh, well, the xy coordinate has to satisfy both equations. It satisfied the first equation, but it didn't satisfy the second equation, so we will write not a solution. Okay, this point is not a solution. Okay, let's try this again with a different point. So x is -4 and y is -3, and we're going to input them for x and y in the equation. And so I start writing it, and I get, well, -4 minus -3, and I set it equal to -1. And then 2 times -4 minus -3, I set that equal to -5. Great. Well, we're questioning, is that true? Do they equal each other? Let's clean it up. -4 plus 3 is -1. So I get -1 equals -1. Check, it worked. But we need to check the second equation. So 2 times -4 is -8, and -8 plus 3 is -5. I get a statement that says -5 equals -5. All right, look at that. So both equations are true in this case. So I will say this point, negative 4 comma 3, this is a solution. All right, so we have found a solution to the system of equations. It's negative 4 comma negative 3. Great. And so you could always check any point you want to in a system of equations to see if that point is a solution. It's a great thing to check when you've solved the system that we're going to talk about here as we move forward. So there are many ways to solve systems of linear equations, and today we're going to talk about 3 different methods for solving systems of equations. And we're going to begin by talking about solving a system of linear equations by graphing. And here's a how-to step process for doing that. So when we want to solve by graphing, step 1, graph the first equation. Step 2, graph the second equation on the same rectangular coordinate system. Step 3, determine whether the lines intersect, meaning they cross each other, are parallel, meaning they never cross each other, or if they're the same line. And step 4, identify the solution to the system. Now, the solution is one of 3 options because they either intersected, were parallel, or are the same line. Well, if the lines intersect, identify that point of intersection. This is the solution to the system. If the lines are parallel, then the system has no solution. And if the lines are the same, the system has an infinite number of solutions because they touch in infinite points. Great. Well, let's dive in to this example 4.2, and we're going to solve this system by graphing. And so we've got 2 linear equations, and we can graph them as lines on this coordinate system. But currently, these equations are in standard form. Standard form is where x and y are both on the same side of the equal sign and the constants on the other side. Okay, so in both these equations, they're both in standard form. Now, our favorite form of graphing a line is slope-intercept form, and that means it's solved for y. So we need to solve these 2 equations for y, and to get y alone, you can think, oh, I could just, in the first equation, subtract 2x from the left side to the right side. And so reorganizing this equation would be simple. It's just y equals negative 2x plus 7. And you're asking, why is it negative 2x? Because I took positive 2x and I subtracted it from the left to the right-hand side of the equation. I'm just moving around my terms. Great. So that one's solved. Let's go ahead and graph that right away. Why is slope-intercept form so great? Because we see the y-intercept, 7. And so I plot the y-intercept first. And then we also see the slope. And in this case, the slope is negative 2. Meaning rise over run would be negative 2 over 1 because, you know, anytime I have an integer, I could always divide it by 1 to see that fraction. Okay, so rise over run is down 2 over 1, and I'm ready to plot from the y-intercept. So I'm going to go down 2 from the y-intercept over 1, and then again, and again, and again, and you see the pattern emerge very quickly. Great. Here I have all of the points that are on this graphing window, and I connect them all with a straight line. And there I go. I have graphed the first equation. Next, I then look at the second equation, and I notice it's in standard form. And so strategy for you is we want to solve for y. So we're going to subtract this term with x in it to the other side. And I'll write everything at that point. So I now have negative 2y equals negative x plus 6. And then I haven't gotten y by itself yet. I still have negative 2 multiplied with it. So I'm going to divide by negative 2 from left to right. Okay? And rewriting this equation cleaned up, here's my final answer. Y equals, well, positive 1/2 x minus 3. Okay? And, you know, negative 1x divided by negative 2 is positive 1/2 x. We like to pull the x outside of that fraction of 1/2. And then 6 divided by negative 2 is negative 3. And so now, this is in slope-intercept form. I can see the y-intercept and I can see the slope. So let's plot the y-intercept at -3, and let's apply the slope of up 1 over 2, rise over run. And finishing off this graphing pretty quickly here, we can see, okay, this line goes whoop, like that. And we have graphed both lines. And now the final question is, where do these two lines intersect? Right? Where do they touch? And the location is right here. We can see it, and it's a lattice point. So the x value is 4 units to the right from the origin, and the y value is 1 unit down from the origin. So we can write the solution to this system as 4, -1. We did it. We just solved this system of equations by graphing. Well, let's go ahead and move forward and look at a variety of other examples. So here's example 4.3. Solve this system by graphing. Okay, looking at the equations, I notice, well, they're both in standard form again, so I will quickly put them in slope-intercept form. I'll make the first equation blue. There it is. Oops. -1. Great. Y equals -3x minus 1. I'll go ahead and graph that really quickly. I go to a y-intercept of -1, and then I apply the slope of -3 over 1. So I'm going down 3 over 1, rise over run. And then I apply it going backwards, right? So what if I continued this the other way? I now see my line, and I just go through that graph with a straight line, and there we go. Now I look at the second equation, 2x plus y equals 0, and I want to solve it for y, to put it in slope-intercept form. So I subtract 2x from the left side to the right side, and I get that -2x there, and then there's that plus 0. All right, now whenever we have addition by 0, we can make it invisible. So it could be made invisible there. But what's nice about having that plus 0 is that it shows me the y-intercept. Okay, so the y-intercept is 0. And so I go to 0 on the y-axis. Okay, and now I'm ready to apply the slope. So from here I'm going down 1 over 2. Sorry, down 2 over 1, right? The slope is -2. Down 2 over 1. Do it again, down 2 over 1. Do it again, down 2 over 1. And so you see I've started to write that line. Now let's do it the opposite way. So from there, let's go backwards, up 2 over 1 to the left, up 2 over 1 to the left, and then up 2 over 1 to the left. And there we go. So it seems like our lines are pretty close to each other, right? But they're not parallel, they're not the same line. They have an intersection point, and we can see that intersection point right here. And that location as an xy coordinate is, well, from the origin, left 1, so -1 for x, and then up 2, +2 for y. I now know that my solution to this system is -1, 2. All right, we have found the solution to the system of equations. It is the only coordinate in all of space that is a solution to that system. Let's go ahead and move forward to our next example, and that is example 4.4. Now, sometimes things are nice and they're written already in slope-intercept form. So this first equation is in slope-intercept form, making my life really easy. I'll put it in blue. First, I plot the y-intercept, and then I apply the slope, up 1 over 2, up 1 over 2, right? A slope of 1/2, it's positive, so I know it goes up from left to right. All those details you learned about lines already. Okay, and so now we look at the second equation, and yep, it's in standard form. Time to put it in slope-intercept form. So I'll talk you through the process really fast. Well, we're going to subtract x from the left side to the right side to start to get y alone. And so I get negative 2y equals negative x plus 4. Okay, and now, yeah, I'm going to divide by negative 2 from the left side to the right side. And now I've solved this for y. And I find out, hey, y is equal to 1/2 times x, and then minus 2. Okay, so let's go ahead and graph that. Okay, so I go to negative 2 on the number line, and then I apply the slope. I go up 1 over 2, up 1 over 2, over and over again, and then down 1 over 2 to go the opposite way. And I put a line through all those points, and then I notice something. Wait a second. These lines do not touch each other, and they always stay the same distance apart. Why is that? Because they have the same slope. Remember, two lines are parallel if they have the same slope and different y-intercepts, which is the case here. Okay? And so we will write that there is no solution. Since these lines never touch each other, there is no solution to this system of equations. Example 4.5. We'll try this one more time, graphing a system. So, I start out and I see my system, and I notice the first one's in slope-intercept form. Great. Let's go ahead and graph it right away. So I'm going to do that in blue. I go to negative 3 on the number line, on the y-axis, I should say, and I apply the slope. It's up 2 over 1, right? Positive 2, 2 over 1. Okay, and so here I go, and I apply it going backwards as well. And there's my line. And next, I look at the second equation, and I need to graph that, but I notice immediately it's in standard form. Let's do a little bit of work. This is great practice for you, by the way, to practice converting from standard form to slope-intercept form. So I want to solve for y. And so I take my term with y, I keep it over here, but I take this negative 6x and I add it from left to right. So I'm going to now have a positive 6x, and then I still have that negative 9 constant. Okay. Now I divide by 3 from left to right. And I can clean this all up. So I'm taking 6 over 3, which is 2, right? So I get 2x. And then I'm taking negative 9 over 3, which is negative 3. Great. So I get an equation that says y equals 2x minus 3, and I have to graph it. Okay, I will graph that in red. And so I go to the y-intercept of negative 3, and I plot a point. And then I apply the slope of 2, right? 2 over 1. Rise over run, 2 over 1. And so I start plotting the points, and I start realizing, wait a second, I'm plotting the exact same line. In fact, these two equations were the equations of the same line, but it wasn't immediately apparent because one was in slope-intercept form and the other was in standard form. But when I put the standard form equation into slope-intercept form, I then realize, wait, this is the same line. And the same line has the same slope, right? 2 is the slope for both, and the same y-intercept, negative 3. Great. So what is the solution to this system then? Well, there are infinite solutions. And it'll make sense now, perhaps visually, because there are actually infinite points on those lines touching each other. So every little point on this graph is a solution to the system of equations. Great. All right. So just a quick recap with graphing. We saw, hey, we could have a system of equations where there's one solution. It's just where the two lines intersect, there's one solution, right? So we saw that, and we saw it again. There was just one solution. It's where those two lines intersected. Or we could have parallel lines, and in that case, there's no solution. And we could also have the same line in which there are infinite solutions. Okay, so we've talked about all the cases, and that's why we kept doing these graphs. Well, let's move forward, and we're now going to discuss a couple new definitions. So coincidence lines have the same slope and same y-intercept. And so these two lines that we just discussed here and here, those we call coincident lines. They are the same line, they're coincident. And then discussing consistent and inconsistent systems. Well, a consistent system of equations is a system of equations with at least one solution. An inconsistent system of equations is a system of equations with no solution. So going and looking back, this system of equations here, because it had no solution, we call that inconsistent. But any system that has solutions, like this one had a solution, it had a single solution, and this one has infinite solutions, so it does have solutions. So that we call consistent systems, right? So we have consistent, meaning there are solutions, and inconsistent, meaning there aren't any solutions. So example 4.6, without graphing, determine the number of solutions and then classify the system of equations. Okay, so we're going to look at two different systems here. And diving in here, we're not going to graph them, but we're going to figure out, how many solutions are there to the system. Okay, and I see this one's in slope-intercept form. This one is in standard form, so I will quickly convert. Okay, I'm going to convert this one here to slope-intercept form. It'll happen pretty fast this time around because we've practiced that a lot. So I end up with negative 2y equals negative 6x plus 12 because I've subtracted 6x from left to right. And now I'm dividing by negative 2, and so I find out, well, the result is positive 3x minus 6. Okay, so I've converted from standard form to slope-intercept form pretty quickly here, and now I can compare my two equations. And recall, parallel lines have the same slope, which these two lines do, but different y-intercepts. So these two lines in the system are parallel lines, and parallel lines do not touch each other. So there are no solutions to this system, right? No solutions. I didn't even have to graph it. I just could think about it conceptually because I could see the two lines in slope-intercept form were parallel to each other. And so we call a system that has no solutions inconsistent. Okay? So this system is inconsistent. Let's just say inconsistent. How's that sound? Okay? Great. Let's try the second equation here. I have 2x plus y equals negative 3 and x minus 5y equals 5. And I notice they're both in standard form. Okay, so quickly we can solve this one for y here, and we get y equals negative 2x minus 3 because all I did was subtract 2x from the left side to the right side, and there it is now. And then I solve this one, which I get negative 5y equals negative x plus 5. What have I done? I've subtracted x from the left-hand side to the right-hand side of the equation. And now I need to divide by negative 5 on both sides. And I'm going to clean it up, okay? And I'll get y equals Well, 1/5 x minus 1. Great. Well, looking at these two equations, this first one in slope-intercept form and the second one in slope-intercept form, they do not have the same slope and they're not negative reciprocal slopes. Okay, so they have different slopes and different y-intercepts. Therefore, there will be one solution because they will cross each other. So I'll say there's one solution. It'll be an ordered pair. And this system is consistent because there's a solution. Okay, so anytime you have different slopes, then you know for sure that these lines will cross each other at somewhere in space. As long as they have different slopes, they will cross each other, and there is one solution, and that means that this system will be consistent. Awesome. Well, let's move on to our next objective. Our next objective is to solve a system of equations using substitution. All right, so we're going to move away from graphs and trying to visualize this, and how would we solve it algebraically with algebra? Well, here's a quick 6-step process that you can follow, and you'll see me execute the 6-step process as I go. Step 1, solve one of the equations for either variable. Step 2, substitute the expression from step 1 into the other equation. Step 3, solve the resulting equation. Step 4, substitute the solution in step 3 into either of the original equations to find the other variable's solution. Then write the solution as an ordered pair. And then step 6, check that the ordered pair is a solution to both original equations. So just like we did on our very first example today, we could take our resulting xy coordinate that we found and plug it back in to make sure that we are right. Okay? Now, step 6, for time's sake, I am not going to be going over step 6, but you can always check once you find a potential solution. So here's example 4.7, and I'm going to talk you through that exact process. So step 1 was to solve the equation for one of the variables. Right now, the variable terms are on the same side of the equation because it's in standard form. And so what we have to do first is solve for either x or y. So looking at this, I could either solve this equation for y, that would be really easy to do, or I could solve this equation for x. It's your choice. So I'll just solve the top equation for y, because I'm used to solving for y to put it in slope-intercept form. That's nice and easy, right? So y equals negative 2x plus 7. Okay. Well, at this point, I know what y is. Y is this stuff. And so when I see y in the second equation, I can plug the stuff y is in for y. So this is called substitution. Okay, so I'm going to take this negative 2x plus 7 stuff, and I'm going to actually plug it in right there for y. So we rewrite this equation. All right, so the second equation gets rewritten, so I start writing x minus 2, and when I see y, I turn it into what y is equal to in the first equation. Negative 2x plus 7, and that's equal to 6. Now, what have I done? I have just substituted in an expression with x for y, and now I don't have any more y's in the equation. All I have is the variable x. And that's awesome because now I can solve for x. And so I would distribute this negative 2 into both of these terms. I'm going to start solving for that variable x, and I get x plus 4x minus 14 equals 6. Combine like terms, move the constant to one side, and the variable terms stay on the other side in this case. Okay? And so here I go. I have 5x, right? Combining those like terms becomes 5x. And then, I would be adding 14 from left to right, and 6 plus 14 is 20. So I get 5x equals 20. And now I divide by 5, and I find out, well, x equals 4, because 20 divided by 5 is 4. I have now found the solution for the x variable. Well, next, I now need to solve for the y variable because I have x and y in the ordered pair, which is the solution. So I'm going to take my answer and I'm going to plug it in right here to get the answer for y, right? So I want to know what y is. It's negative 2 times 4, because x is 4, plus 7. Okay, so I'll write that out. Y equals negative 2 times 4 plus 7, which is negative 8 plus 7, negative 1. Great. So I now know that y equals negative 1. And so how do we write our answer? Well, we said we write it as an ordered pair, x, comma, y. That is the final solution. It's that xy coordinate in space. If I was to graph this, then 4 comma 1 would be the intersection point of these two lines. We should try this again. So I'll walk you through the process again in example 4.8 and make this nice and big here. There we go. Solve this system by substitution. Now, when I look at the system of equations here, I see 4x, a 2y, a 6x, and a negative y. Well, I always try to look for the easiest variable to solve for. And in this case, I would say negative y is the easiest one to solve for. In fact, I could add y from left to right and subtract 8 from right to left, and I would have solved for y. Okay, so always look for the easiest variable to solve for. So I'll show you explicitly what I'm doing. I'm adding y from left to right, and I'm also subtracting 8 from right to left. And so now I've solved for y. Y equals 6x minus 8. Cool. And you could think about that for a second and make sure you understand how that just happened, or you could solve it in a different way, right? What you could do is subtract 6x from left to right and then divide by negative 1, and then you would have solved for y as well. So here we go. We have now gotten the variable y by itself. Y is 6x minus 8. And now we can apply a substitution. We're going to take 6x minus 8, that expression, and we are going to substitute it in right here in the first equation for y. So rewriting the first equation, I have 4x plus 2 times y, which is 6x minus 8. I'm substituting, equals 4. And what's so great about substitution is it makes it so this equation only has one variable, the variable x in this case. And now we want to solve this equation that we've created for x. So we distribute, and we get 4x plus 12x minus 16 equals 4. And then we combine like terms and move the constant to the other side. Like here I'll add 16. And I now combine 4x plus 12x to get 16x. And so I get 16x equals 20. And lastly, I divide by 16. Okay, I'm now dividing by 16 from left to right. Okay, and I've solved for x. X equals 20 over 16, which is a fraction that reduces to 5 over 4, because 20 and 16 are both divisible by 4. 20 divided by 4 is 5, and 16 divided by 4 is 4. I have now found x. Yes, our solutions can be fractions. Yeah. Okay, now that I have found x, my goal is to solve for y. So I need to find y by plugging this value I found for x in right there, right? Because this equation solves for y. Y is 6 times x, which is 5/4, minus 8. And so here I go. Y equals 6 times 5/4 minus 8. And let's see, 6 times 5 is 30. 30 divided by 4 doesn't come out quite clean. Yeah. 30 divided by 4 is 15 halves. So I'm going to write it as 15 halves. And then 8 is 16 halves. Agreed? 8 is the same thing as 16 divided by 2, so I can write 8 as 16 halves. Why did I do that? Because now I have the same denominator for the fractions, and I can subtract them easily. Because 15 minus 16 is negative 1, and then the denominator stays the same. So I have just found y equals negative 1/2. Great. And I now know x and I know y, so I will write my final answer as an ordered pair. My final answer is 5/4, comma, negative 1/2. Done. All right, so we've just talked you through this short process with these two examples of how to solve a system of equations using substitution. Let's move to our next objective of the day, which is to solve a system of equations by elimination. Okay, so how do you solve a system of equations by elimination? Follow this 7-step process. Step 1, write both equations in standard form. If any coefficients are fractions, clear them. To clear fractions, you might recall, to clear fractions, we need to multiply an equation by the LCD, the least common denominator, and that will clear the fractions. That we talked about in many previous lessons. Step 2, make the coefficients of one variable opposites. Decide which variable you will eliminate and multiply one or both equations so that the coefficients of that variable are opposites. Great. Step 3, add the equations resulting from step 2 to eliminate one of the two variables. Step 4, solve for the remaining variable. Step 5, substitute the solution from step 4 into one of the original equations to solve for the other variable. Step 6, write the solution as an ordered pair. And of course, step 7, you could check whether that ordered pair you just found is a solution by plugging it into both the original equations and checking to see if they're true. Great. Well, let's go ahead and look at a couple of these examples. I'm going to show you that 7-step process. Example 4.9, solve the system by elimination. Okay, here I go. So the goal is to make it so that one of the variables has the same coefficient with opposite sign. So if I see 2x, I would want x to be negative 2x. Okay, or if I see y, I could make, something else negative y. Okay, so you've got to think for a second, and then you realize you could multiply the equations by anything you want to, and it's the same equation. For example, if I multiply this bottom equation by negative 2, okay, so just take negative 2 and multiply it, okay, into everything. You could do this. This is something that you're allowed to do, and it's really the same equation. It's an equivalent equation. So I'm going to do that. I'll rewrite the top equation for this system. It's 2x plus y equals 7. And then negative 2x plus 4y equals negative 12. Okay? I have just multiplied negative 2 into, negative 2 times x, negative 2 times negative 2y, and negative 2 times 6. And I rewrote the equation like this. And what's so cool about that is you can now take that system of equations and do stacked addition to it. And it eliminates one of the variables because 2x plus negative 2x cancels. The x variable has been eliminated. We just used elimination. Okay. And now do stacked addition to the rest of the equation. Y plus 4y is 5y, right? 1y plus 4y, definitely 5y. And 7 minus 12 is negative 5. And so now I divide by negative 5 from the left side to the right side, and I find out that y is equal to 1. Okay. Right? Because negative 5 divided by negative 5 is positive 1. And at this point, you can take your answer that you got for y, and you could plug in that stuff into either of the two original equations. So I'll take the top equation that says 2x plus y equals 7, and I'll solve it for x when I input 1 for y. Right? So we're going to input our answer for y that we got, and we write 2x plus 1 equals 7. Now, this y, I know y equals 1, so I replaced it with 1 in the equation. And now I'm going to solve for x. So you can see clearly this linear equation is being solved right before your eyes. And 7 minus 1 is 6. And I'm dividing by 2. And I have now found that x equals 3. Great. Well, how do we report our final answer? Well, that's as an ordered pair. X comma y. So our solution is 3 comma 1. Great. All right, so what is the goal of the elimination method of solving a system? The goal is to multiply one of the equations by something, or you could even multiply both of the equations by something so that you get the same coefficients for the same variable with opposite signs, right? I saw 2x and I saw x, so I multiplied this equation by -2, and that caused me to be able to eliminate the x variable, and now I only have one variable which I can quickly solve. I then take that variable, I plug it into one of the two equations. I decided to do the top equation, but it doesn't matter. And I solve then for x, and I now have my final solution, 3 comma 1. I think we should try this again for good measure. So here's example 4.10, solve the system by elimination. And I see 4x minus 3y equals 9, and 7x plus 2y equals -6. And I think, how could I make it so that both of the variable terms, either 4 and 7 and -3 and 2, become the same coefficient, opposite signs? And if you think about it long enough, you would come to the conclusion that you could take the top equation and multiply it by 2, and take the bottom equation and multiply it by 3, and you'll see what happens. Okay? So we're going to rewrite everything multiplying by 2 in the top equation and 3 in the bottom equation. And the more you practice this, the better you'll get. So we rewrite the two equations as 8x minus 6y equals 18. And the bottom equation, 21x, and then plus 6y equals -18. And now we can do stacked addition to the two equations. It's this cool thing. You didn't realize you can do this, but you can. You can do stacked addition to the two equations. Okay, and what you'll notice is that I now have -6y and positive 6y, and when I add them together, they cancel each other. So these y variable terms cancel. And all I'm left with is 8x plus 21x, which is 29x. Let's do it in blue. 29x. And that equals 18 plus -18, which is 0. And now I divide by 29. Let me do it in red. And I now have that x equals 0 over 29, which 0 over 29 is just 0. Okay? And now that I have found x is 0, I can take that and plug it into one of the two original equations. Okay, so just clearing this up here a little bit, I can take this x and plug it into the top equation or bottom equation, doesn't matter. Like, I could plug it in right there. And so plugging that in, I get 7 times 0 plus 2y equals -6. And then 7 times 0 is just 0. And so I have 2y equals -6, and I divide 2 from left to right, and I find out that y is equal to -3. Solved. There we go. And so the solution to the system of equations is x comma y, in other words, 0 comma negative 3. That's my solution. All right, so you can see what we did in this case to solve was we had to multiply the top equation by 2, okay? And then the bottom equation we multiplied by 3. And that made it so that we could eliminate the y variable. The y variable was eliminated, and all we have is the x variable, and we continue to solve. Plug the value you find into one of the two equations. I chose the second equation, and then solve for y, and now you have the ordered pair. That is the solution to this system of equations. Moving forward, we're going to look at some other examples, and we're just going to keep practicing this a little longer. This requires practice. And so here I see a system of equations that has fractions for coefficients. And if you want to clear fractions, you have to multiply everything by the LCD, the least common denominator. Now for the first equation, the LCD is 2 because that's the only denominator. So I look at the denominators and I say, well, the LCD of just 2 is 2 itself. And now looking at the second equation, what is the LCD of 2, 3, and 2? Well, the least common denominator of 2 and 3 is 6. 2 times 3. And so now if I multiply the LCD that I found into all of the terms, then I will clear fractions. No more fractions to worry about. That's a wonderful thing. So I'll rewrite everything. I have 2x plus y equals 12. And I have 6 divided by 2, which is 3 times 3, 9x. Plus 6 divided by 3, which is 2 times 2, 4y. Equals 6 divided by 2, which is 3 times 17. And 3 times 17 is 51. Okay, so I have just cleared all my fractions. That's awesome. That makes me feel good. Okay, and now I'm going to check, hey, how would I use elimination in this case? And I think for a second here, and I say, well, if I multiplied this top equation by negative 4, then I'd get negative 4y here, and then I'd add it with 4y, and I'd be eliminating the y's. So that's what I'm going to do. I'm going to multiply this top equation by negative 4. Okay, and so I'm going to rewrite this whole thing now, distributing negative 4 into all three terms, and I get, well, negative 8x, and then minus 4y, and that equals negative 48. And then I rewrite the bottom equation. I didn't do anything to the bottom equation, I'm just rewriting it. And at this point, we are very happy because now the y variable cancels, and I get negative 8x plus 9x, right? I'm going to do stacked addition to this equation. That's the coolest thing ever. We can do stacked addition to two different equations and get a new equation. Negative 8x plus 9x is 1x. And negative 48 plus 51 is 3. And so I have now found the solution, x equals 3. And another detail that is good to know is we could plug this into any of the equations that we used along the way so that we can find y. So we could plug it into this x into this equation, this equation, this equation, this one, or this one. It doesn't matter. And my suggestion is that you plug it into this one. Okay, so I have 2x plus y equals 12, but I'm going to take x and replace it with 3 because x is 3. Great. And so I end up with 6 plus y equals 12. And I subtract 6 from left to right. And I find out y equals 12 minus 6, which is 6. And to finish off everything that we've done, we simply write an ordered pair. The solution to this system of equations is 3, 6. And we're done. Example 4.12. Solve this system again by elimination. Okay, so I see a system and I see a fraction in there. So I'm going to multiply the bottom equation by 4 because I see the denominator, the only denominator is 4. To clear the fractions, I multiply by 4. And then I distribute to all of the terms of the equation, and I get, well, 4y equals 12 minus 3x. There I have it. But my goal is to put this, this system, both of the equations, in standard form. Okay, so usually we're trying to convert from standard form to slope-intercept form if we're graphing, because that's great, or even if we're using substitution. But for elimination, we want to put both of the equations in standard form. And so putting this in standard form, I would add 3x from right to left. Because standard form is getting all of the terms with variables on one side of the equation. And I would have 4y plus 3x equals, well, let's write it like this. Make it easier. 3x plus 4y equals 12. Great. Okay, so I have just taken the second equation, and I wanted to clear the fraction, so I multiplied 4. I got this. Then I wanted to put it in standard form, so I added 3x from the right side to the left side, and I got this. And now I look at my first equation, 3x plus 4y equals 12, and I look at my second equation, 3x plus 4y equals 12, and I say those are the exact same equations. They are exactly the same. In fact, they are the same they're the same line repeated twice. And if they are the same line, graphically, they would be stacked on top of each other, and you would have infinite solutions. Okay, so there we go. There are infinite solutions to this system of equations because we cleaned up the bottom line little by little, and we found out it's the exact same line as the top line. Now, we'll just finish off today with this last little piece because you've learned 3 different methods for solving systems of equations. You've solved by graphing, you've solved by substitution, and you've solved by elimination in this lesson. And we did a lot of examples. So this very last example, 4.13, for each system of linear equations, decide whether it would be more convenient to solve by substitution or elimination, and then explain your answer. All right, so who decides which method to use to solve? You do in the end. So you could take any of these systems that we looked at and you could solve them with any of the 3 methods we've discussed. It doesn't matter. Okay, so take your pick. You just need to pick the best strategy. And sometimes one type of method is easier to do than the other based on the equations you see. So, looking at part A, I look at this and I say, well, what if I was to multiply this bottom equation by 2? Then I could eliminate the y variable. And so, for me, I'm going to say the elimination method is the most convenient method. Because I look at the equations and I quickly see if I multiply one of the equations by a value, it would eliminate one of the variables. In this case, if I multiply the second equation by 2, then it causes this negative 4y to become negative 8y, and the positive 8y will cancel the negative 8y when I do stacked addition of the equations. Great. And I look at the second system of equations here, and I see one of them is already in slope-intercept form, right? Well, one of them is already solved for y. In other words, I could substitute this stuff in right here for y. I could substitute really easily, really fast. So I'm going to say the best method to use in this case would be the substitution method, because one of the equations is already solved for a variable, right? This equation was already solved for the variable y, which I can just take this stuff and plug in for y in the top equation and then proceed. There you go. So sometimes there is a clear, easier method to get what you need done. And it's just on a case-by-case basis. So you just have to look at the system and then make a decision on what the best method will be. This has been lesson 4.1, and I hope that you have a wonderful day. Thank you.